Hello, everyone. I'll stand back here. I'm Noah Prezant. I'm with Collier Aerospace, and I'm here to introduce Blake Berk. Blake Berk has spent his whole career at Radia developing the WindRunner. After graduating from MIT in 2019 with a degree in aerospace engineering, Blake began his work on Radia's structures team. Blake quickly developed a passion for automating repetitive processes and has written many hypersizer scripts and automations to increase capabilities, tailor processes, and push the software forwards. This includes anything from templating to parallelization to more efficient structural optimization. So please join me in welcoming Blake Berk.
Thank you, Noah. Thank you, everyone. Thank you for having me. Really excited for the opportunity to talk more about WindRunner. We were in stealth mode for the first 6 years of my time at Radia, and so it's really a great opportunity anytime I get to speak publicly and share what we've been up to for so very long. Today, I did have a slight title change to my presentation. It was originally a little bit more focused on the automation, but I changed it to a little bit more just about WindRunner and kind of our design philosophy with hypersizer and HyperX. But I still love the automation aspect, so find me after or tonight if you want to talk more about automation, especially with hypersizer. With that being said, the normal legal junk, we do not have any WindRunners to date. Anything that you see is computer generated. So Radia, WindRunner. Radia is the company producing the WindRunner aircraft. The aircraft is designed for 3 key verticals, with our primary focus being onshore wind energy. The intent is to provide a step function in the onshore wind energy market by enabling the transportation of blades up to 105 meters in length. For the defense and commercial cargo industry, Radia and the WindRunner provide an unprecedented payload volume to transport existing aircraft or any other types of cargo that need large volume but not necessarily high mass capability. This unprecedented space enables transport of vehicles like 4 F-16s, wings on, no modifications, just put them on the aircraft and they're ready to rumble. Up to 6 V-22s, as pictured in the far right, and I think we can even do 2 Falcon 9 rockets at the same time. So we're talking a very massive aircraft, and providing this capability to reduce the number of flight hours to transport aircraft around the country or around the globe even. Ultimately, this is also a new solution. If you're familiar with a lot of the existing military cargo aircraft, they were designed in the 60s and last produced in the 80s or even early 2000s for something like the C-17. So we're providing a new modern aircraft overall for these different use cases. Focusing in on a little bit more of wind energy, I really only have one slide explaining why bigger is better for wind energy, but there's a lot to it, and I'll try to cover a few aspects here. The first and obvious thing is that the rotor diameter is significantly increasing. For all of the engineers in the room, we have a pretty simple power equation on the far right. As you increase the length of the blade, or the radius of the blade sweep, you're now getting an exponential increase in the power potential being generated by the wind turbine. Equally important, you can also generate the same level of power, but at a lower wind speed. This enables much more acreage of the globe that becomes viable for wind energy because you have lower power. Ultimately, the economics of the large onshore wind market are due to the higher power generation, the fewer components that you need to manipulate, easier grid, higher hub height. There's many aspects that all get better when you go bigger. So how big are we actually talking when we say 105 meters or these towers? We're talking blades that are nearly the length of a Saturn V rocket and installations with the tower that are starting to rival the Eiffel Tower. So these blades are massive, the installations are quite large, and the question is, how do you transport them? Current terrestrial transportation is quite a mess. It can take months or even years to plan a given route to deliver a blade from the factory or the port where it arrives to the land infrastructure, and then having to deliver it all the way to the wind farm itself. What's shown here is just a 70-meter blade, and so you can only imagine what adding another 30 meters does to any tight turn as you navigate a small town. Today's routes often involve knocking down streetlights, taking down power lines, even displacing buildings just to enable a critical junction in the route to deliver an aircraft. But it's not just the length, it's also the height and the width. Of course, this is a structures presentation, so as you increase the aerodynamic loading along the length of the blade, as well as a longer blade with more mass, you now have a higher root bending moment. And so the efficient way to react that is with a larger base diameter, which now starts to push on constraints like tunnels or bridges or overpasses that you have to traverse under. So the easier, quote unquote, solution is to fly them, which is what Radia is aiming to do with the WindRunner. The WindRunner is optimized to handle encompassing a blade entirely, so up to a 105-meter blade with a mouth that is roughly 28 feet in width and height. So probably easily defeating this wall here that we're presenting on just in the mouth of the WindRunner itself. But importantly, volume is not our only requirement. In addition to volume and all of the capabilities with the payload itself, an important aspect of our company is to deliver the blades directly to the wind farm. And so that involves operating on semi-prepared runways where we can build just a dirt strip at the wind farm itself, land there, drop the payload, and return to grab the next blade for delivery. With our massive wing, which doesn't always look so massive because of the comparison to the fuselage, we're talking a wing and a massive flap that enable the WindRunner to approach a landing at speeds that rival a small business jet, so not comparable to any of the large transport category aircraft today. So why does our fuselage look the way it does? And that's just to fully encompass the various blade configurations that we're designed to carry. We can transport one full ship set of 3 blades up to 80 meters in length. So that's roughly the limit of ground transportation today. We can do that all in one. As we go larger, we can carry 2 blades up to 95 meters or 1 blade up to 105 meters long. While it may seem inefficient to transport only 1 blade at a time, from the time perspective, reminder how long it takes to transport a blade via ground. Flying an aircraft, even a slow one like WindRunner, is way faster than trucking them from port to wind farm. And then as far as the economics of going larger, you just get so much better potential with a larger blade that there's really not something to worry about when the blade will be operating for years and years, and transportation is just 1 day. Really hammer it home in terms of our scale. We have a nice 6-foot-tall person and a 45-foot school bus that really don't compare to the length or size of WindRunner. A quick fun fact for our horizontal tail: the span of our horizontal tail is roughly comparable to the wingspan of a 737 Classic. So massive tail, much bigger wing. Comparing to other aircraft, I'll start on the right side. You can fit an entire A380 fuselage in our forward portion of our aircraft and still have room for an entire A320 in the aft portion, and that's accommodating both length and the width of those vehicles. But really the important thing here, as I transition to a little bit more of the technical aspects of the design of WindRunner, is where we are comparatively in payload density. WindRunner is a true new class of aircraft design. All of the other cargo aircraft follow roughly the same payload density. It's only when you look at WindRunner that's truly off the map that you begin to question the conceptual design, like many of the unique concepts that we've heard about here at the HyperX conference. We have an aircraft that is many ways the same. It's a pretty basic aircraft. We're taking a very low risk approach. We're not inventing anything new or limited technology development overall. The only thing that's unique is the scale and the mission. And so when we think about this mission that doesn't quite follow the standard parametric design, that's where we had to kind of get a little bit more creative, or at least start doing the math for how to do the conceptual design of the aircraft. And that's where we quickly went with the GFEM approach. In kind of the first year of Radia's design of WindRunner, we started the GFEM in order to accurately estimate the structural weight and make sure that we can achieve that loads and structure convergence. But we faced all the problems of being a new company that doesn't have any existing tool chain. We had all the textbooks still on the wall that everyone else has for kind of the standard textbook methods. We had some of the more or less publicly available allowables from MMPDS and NCAMP. And we had the calculator, the finite element analysis tool to conduct accurate or more detailed sizing of a product. But we did face some limitations, namely manpower. Back when we first started using Hypersizer in 2019, we really only had 1.5 to 2 full-time equivalents of stress engineers at the time. We definitely did not have any tool chain, let alone a tool chain that was customized for our use case. We had no testing and no data to support any of our use of failure analyses or any other methods. And we had no integrated processing of our finite element analysis or way to go from loads to a sizing result. Which, of course, the punchline, which is where HyperX came into play. It provided all those building blocks, but also created kind of an integrated solution that allowed us to bring everything together. You'll notice that I also changed textbook methods to extensive methods because we went from a tool base that now included smeared panels, various different cross sections, discrete sizing, and everything in between, really enhancing what we had to work with in our toolbox. All this becomes important because, again, we have a massive aircraft. Miles and miles of stringers. We have 7 miles of stringers just in the fuselage. I tried to come up with a comparison. I came up with the Golden Gate Bridge, the 1.7 mile long Golden Gate Bridge. End over end, our fuselage stringers map nearly to 4 lengths of the Golden Gate Bridge. And when you add in the wing and the tail, you get another 6 full Golden Gate Bridges for over 10 miles of combined stringer length. And again, only 2 analysts when we first got started. Now we're about 6 or 7, so figure a little over a mile per analyst. This is one of the key features that we needed to address and where Hypersizer and HyperX and their family of tools started to fill the void. Starting to talk a little bit more about the automation, we leveraged a customized sizing routine. The intent here was to leverage the API to do anything that would involve manual labor and involve the stress analysts only when necessary. The process starts basically like any other model. We take the GFEM, import it into Hypersizer. We created some customization along that import, really to enforce kind of templating or enforce some standardization and to ensure visibility into the settings we were selected in Hypersizer. Not every stress analyst that we have was familiar with the program, and so we created a tool that would allow people to see a lot of what was inside Hypersizer in an Excel spreadsheet or something comparable. Something that I am very grateful for Steven and his team that we no longer will have to do in the same way. We divided up all of the databases for our aircraft into many tens of databases. And this was done not because we had an army of stress engineers that could tackle each database uniquely. It was because we needed to parallelize the sizing. From there, we entered the sizing loop, where we kind of created our own makeshift hyper FEA. Sorry to steal the trademark if it's a trademark phrase. But we're taking the sizing loop, starting with the same FEA update, FEA solve as necessary, and then entering our kind of unique sizing routine. And this is, again, stealing from Steven. We divided into smaller databases to work harder. This was to enable the computer to solve more hypersizer databases simultaneously. And the sizing loop aspect is us working smarter. And so what we did here was attempted to tackle the problem of candidates. We wanted to size every component with the full design space that we were willing to allow for every single dimension of every single component, but we didn't want to wait for a really small step size to go through from min gauge all the way up for heavily loaded components. And so what we did is we started with large bounds and a large step size. And then from there, again, no FEM update, no FEA solve, we sized again. But the new sizing was done with bounds based on the results of the previous sizing. What that enabled was us to kind of shift the bounds for the actual optimal sizing for each dimension of every component, but do so slowly until we got to a small bounds and a small step size where we were around that local solution, that locally optimal result, but we could do so more efficiently. So instead of having to do 10 million candidates for every component all at once, we could do it in steps of hundreds of thousands of candidates at once. And then only then would we re-update the FEM and continue the kind of standard hyper FEA loop where you do the sizing and then update the loads. Upon completion of the sizing loop, if necessary, we could update the FEM again and provide an Excel database to the rest of the team with all of the critical outputs, effectively a stress report, but in all tabular format. The key point of this sizing loop was to enhance our speed. We needed to go quickly. We have 150,000 elements in our GFEM, 30,000 components. I believe that translates to zones in HyperX, and 400 load cases to consider for our sizing iterations. So again, the intent here was to consider millions of candidates per components, but doing so in a more efficient way where you don't necessarily have to go through each component one by one. Ultimately, we got to an approach where it's not quite 1 minute, but it's a lot more elements and a lot more components, and so we could do the entire GFEM sizing in less than 7 hours, which means that we could do 3 effective hyper FEA loops in less than 24 hours versus a single loop that might take days or even weeks to complete. So ultimately, my last slide here is to point out WindRunner is a unique aircraft in many ways. It's massive and on a scale that's not very seen very often, but we do have a lot of acreage structure, and that was very much what Hypersizer and HyperX have been able to optimize for. Some of the key features for our startup was having the extensive methods and failure analyses. Again, of course, with the availability of the customizable plugins for any additional analyses that we wanted to consider. The FEA processing and exporting, again, just like others have presented today, just the streamlining of and the ease of updating our P shells and P bars, it made it a lot simpler to build up the initial GFEM because you didn't have to focus on all the properties. You could put an unsized model directly into Hypersizer to really kick off the entire GFEM iteration. And ultimately, the automation and customization was critical for us to develop a solution that was ideal for Radia and not just for any generic company. Ultimately, that's enabled us to maintain a quite small team of stress analysts and designers. We've had stable mass properties for years, largely due to a consistent sizing process and iterations, as well as fast sizing iterations and complex trade studies where over the course of the years, we've traded everything from stringer spacing, frame spacing, as well as cross sections and different decisions. So with that, thank you for everyone for your time, and I am available for any questions that you may have. Yeah, so the question, since there wasn't a microphone for this, was what records is this going to set in terms of size of aircraft? This aircraft will be the longest and I believe largest volume fuselage for any existing aircraft. It does not break any records in terms of width because we're constrained by the same things that every other aircraft that's trying to operate out of, I believe it's ICAO Group 6 airports, sorry. So we're designing it to be longer and with more volume, but we won't break any mass records. As you saw on the payload volume chart, we are, sorry, a lot of animations. We're right in the middle of payload mass, so we don't have a shockingly large maximum takeoff weight or anything. It's purely the volume and the length that are making it the world's largest aircraft. But it will be a certified aircraft as well, so Part 25 certified.
When you went from the large to medium to small bounds and step sizes, what was that process like? Was it different design properties? Was it zone overrides? What did you guys use to kind of distinguish each of those?
So we've only implemented this process in hypersizer, particularly due to the inefficiencies of hypersizer relative to the modern HyperX. For that, we really were just attacking the component dimension matrix. And so for each step, we would just simply update the matrix of effectively defining the property candidates to be considered for design. And so we would just step through that, basically extracting the previous result and then perturbing the dimensions for that matrix based on the previous result for every single component.
How are you testing all this, especially at the vehicle level? And have you been out to the gantry here?
Are you referring to testing at the, you're saying at the component level or the aircraft, full aircraft? It'll be at our final assembly site. We'll have a full static and fatigue test article for the full scale aircraft as part of our final assembly plans.
My question is kind of twofold. How does the company go about assessing sort of the market demand for the larger blade? And what's the split between the larger blade and the small blade in terms of current operations?
So for the first part of the question, the company is expecting to effectively take over a certain percentage of the market share. We're not expecting to get 100% coverage for the market share. That doesn't go into our fleet sizing estimations or anything like that. We're expecting to extract basically a certain proponent of the market, particularly where we feel that what we call gigawind at the 105 meter scale is more advantageous than standard wind of today. To kind of address the second part of your question, today's market is largely limited around the 70 meter length for most transportation in the US and Europe. There's a few cases where it can go up to maybe 80 meters in length, but largely you won't see any 95 or 100 meter blades onshore in anywhere other than China.
I don't know if it was in any of your slides, but what is y'all's expected entry into service date?
We hope to be flying by the end of the decade, but kind of certified in the early 30s.
What do engineers at Radia call themselves?
Radians.
Thanks. So, how do you kind of plan on manufacturing this thing? Is it going to be barrels that you're splicing together, or laps? This is a little bit more detailed question, I guess, but I'm just curious.
Both. We'll have many barrels and many skin panels to comprise the entire fuselage, especially.
So heavily composite the whole fuse is going to be composite.
Metallic fuselage.
Metallic fuselage. Okay.
So due to the size of the aircraft, is there going to be any restrictions to the range at which you guys can carry certain cargo?
Absolutely. We are optimized for relatively short range for a vehicle of this size. A typical transport category aircraft can go on the order of thousands of kilometers with payload. WindRunner is specialized for kind of that final blade delivery, where we'll go directly from the factory or the port to the wind farm, which we estimate is going to be on average between 6,000 or 1,000 nautical miles. So that's kind of roughly where our maximum payload range will be. But we're designing it to make sure that we can, when empty, get anywhere in the world. So we can cross any ocean or get anywhere as needed.
And what's the number of like a fleet that you guys will be predicting for like number of aircrafts you guys can make with this?
I'm not sure I'm allowed to say that.
Okay.
You can check our website if so, but it's probably more than you think.
So I think I'll cut off questions here. If we could ask more,
Real quick, before you give, I'm here also with one of my colleagues, Justin Morris, so if you have any questions, feel free to talk with both of us. Yeah.